Hi, welcome back to Differential Geometry. Today's subject is the dot product, which is section 2.1. So parts of this section will likely be a review for you, so naturally I'm going to skip them. And so I'm going to start mid-chapter now with the definition. So this definition is an extension of dot products to tangent spaces. So bring this out. This is the definition. So the dot product of tangent vectors v sub p and w sub p. V sub p and w sub p. And they're at the same point at p of R3. It is the number v sub p dotted with w sub p. That's the notation. It's equal to v dot w. So we just look at the vector parts essentially. So this definition extends from it follows from the canonical isomorphism v to v sub p at each point p in R3. So in other words, using this canonical isomorphism, properties that involve dot products, such as norms, are easily defined. So we can then define the cosine of the angle between two vectors. Okay, I'm going to write this down. We can define the cosine of the angle of the two vectors to be v dotted with w to be norm v, norm w, cosine theta. Or we can just move these to the other side, v dotted with w over norm v, norm w is equal to cosine theta. So we could write it like that as well. So we can see that if theta is equal to pi over 2, then v dotted with w equals 0. Okay? And if this happens, then we say that the two vectors are orthogonal. If this happens, we say that v and w, I should put arrows on top of them, are orthogonal. Okay, I'm going to move on to the next definition. A set E1, E2, E sub 3 of three mutually orthogonal unit vectors tangent to R3, tangent to R3 at P. It's called a frame at the point P. Furthermore, E1, E2, E3 is a frame if and only if E1 dot E1 it's equal to E2 dotted with E2, which is equal to E3 dotted with E3, which is equal to 1. And E sub 1 dotted with E sub 2 is equal to E sub 1 dotted with E sub 3, which is equal to E sub 2 dotted with E sub 3, which is equal to 0. So the first condition is that each E sub I is unit length. And the second one is that each pair of e sub i's is orthogonal. Okay. So of course the dot product is symmetric. So we also know that, for example, e sub 2 dotted with e sub 1, that is also 0. And then the same goes for the other two backwards e sub i's. So equivalently, a different way of writing this, we can write that e sub I dotted with e sub j is equal to the Dirac delta of I and j. Sorry, the Kronecker delta function. So, and we're defining delta ij to be 1 if I equals j, and 0 if I is not equal to j, which is just saying exactly the same thing as what we already had. So as an example, we can say that u sub 1 of p, u sub 2 of p, u sub 3 of p is a frame at p. So, and all I have to do is just remember exactly how these u sub i's are defined. So, for example, u sub 1 is defined to be u sub 1 of p. That's defined to be 1, 0, 0 at p. That tangent vector. Okay. So we can easily check this condition. I'm not going to right now. So the next theorem is pretty similar to what you might encounter in a linear algebra course with regards to orthonormal bases. So theorem, let E1, E2, E3 be a frame field at a point P of R3. P of R3. Okay. So if V is any tangent vector to R3 at P, then V is equal to V dotted with E1 times E1 plus V dotted with E2 times E2 plus V dotted with E3 multiplied by E3. Okay. So for this proof, we want to show that each E sub 1, E sub 2, and E sub 3 are linearly independent. So suppose sum A sub I, E sub I is equal to 0. Where A sub I, each one of them is a real number. So a scalar. Then 0 is equal to sum A sub I, E sub I times EJ. Sorry, dotted with E sub j, which is equal to sum AI, EI dotted with EJ, which is equal to sum AI delta ij, which is just a sub I because we lose all of the j's that aren't equal to I. Okay, thus a1 equals a2 equals a sub 3, which is equal to 0. So we must have that e1, e2, and e3 are linearly independent. Sorry, it should be e1, e2, e3 are linearly independent. So the tangent space has dimension 3 since it's isomorphic to R3. GP of R3 has dimension 3. So in other words, E1, E2, and E3 must form a basis for R3, or sorry, the tangent space at R3. Thus, E1, E2, E3 form a basis for T sub P of R3 because because we have 3 linearly independent vectors, and this space is of dimension 3. So hence, for each vector v, there are three unique real numbers C1, C2, and C3, such that V is equal to some Ci Ei. But then we can write V dotted with E sub j is equal to some Ci Ei dotted with E sub j, which is equal to some Ci delta ij, which is equal to Cj. Okay, so then we can write that V is equal to some V dotted with E sub I times E sub I. Okay, so this is just C sub I. And if we go back to what we want, well, if we go back, we can see that's exactly what we want. It's because this is some Ci E sub I. Going back to the definition, or the theorem. And this is exactly what we got. So this is a complete proof. Okay, well, that's it for today. Thanks for listening.